All right, in this section, we're back to thermodynamics. We're back to our good friends, Gibbs free energy and entropy and enthalpy. And so hopefully when you reviewed all these concepts on the physics classroom in the lesson yesterday, hopefully all that came back to you to summarize things. And these are trends that you really need to have them memorized. Because if you don't, you're really going to struggle as you're trying to analyze these different conditions in dissolving. So for Gibbs free energy, if delta G is negative, that means your reaction is going to be spontaneous. If delta G is positive, then the reaction is not going to be spontaneous and it's not going to occur. Okay? Enthalpy, the amount of heat that's given off in a reaction. If delta H is negative, that means it is giving off heat and your reaction is going to be endothermic. It had more heat at the beginning, it's giving heat off, and so this change is negative. So exo means out of. It gives off heat, it's exothermic. Delta H is negative. If it is endothermic, taking in heat, then delta H is going to be positive. Entropy, measure of disorder of a system. The more disordered it is, the more disordered it becomes, the greater delta S is. And so if delta S is positive, it means your entropy is increasing. If delta S is negative, it means your entropy is going to decrease. And remember that in nature, things tend to become more disordered. Now, they don't always become that way. You can force them to go the other direction, but the natural tendency is for things to become more disordered. These three qualities are related in this equation, delta G equals delta H minus T delta S, where T is the temperature as expressed in Kelvin. And remember, Kelvin temperatures are always positive because 0 Kelvin is absolute zero, where all molecular motion ceases. And so therefore, your Kelvin temperature is always going to be positive, right? So we're going to be using this relationship a lot as we go through the dissolving process as to whether we're going to figure out whether these things are going to dissolve, how they're going to dissolve, what the characteristics of that type of solution are going to be. Now, within a solution, we've got three different kinds of interactions between the molecules. The solute molecules are going to react with each other or interact with each other. So they will be attracted to each other or not attracted to each other. The solvent molecules will be attracted to each other. And the solute and solvent will be attracted to each other. And so the strength of those interactions will determine whether dissolving is going to take place and how it is going to take place. So I have three classes of conditions. The first class is when the solute particles interaction with each other and the solvent particles interaction with each other, where those attractions are actually less than the solute and solvent attractions with each other. So what that means is that the solute and solvent are more strongly attracted to each other than the other way around, okay? What that means then is that because these attractions are greater, it means that we're then going to be going from a high energy situation to a low energy situation. And in that case, delta H is going to be negative and dissolving is going to be exothermic. Okay? Second type of situation is where the interactions of the solute particles with each other and the interactions of the solvent particles with each other are equal to the interactions of the solute and the solvent with each other. An example of this one would be if I've got a gas dissolving in another gas. The particles aren't really attracted to each other anyway because they're gases. And so if this situation is true, I have what's called an ideal solution, and the enthalpy change is actually equal to 0. All right. Now, the third type of situation that I'm going to have is if the solute is attracted to itself and the solvent is attracted to itself more than the solute and solvent are attracted to each other. An example of this is something as simple as salt water. In salt water, your sodium ions and your chloride ions are attracted to each other in an ion-ion type of attraction. And if you remember from module 4, that type of attraction is much stronger than an ion dipole attraction, which is what I would have if I have a sodium ion attracted to the negative, partial negative side of the water molecules. That's an ion dipole attraction. And so a situation like this is very much the case in salt water, okay? In this case, I have to, it requires energy for me to be able to shove those molecules together and actually dissolve each other. So that means that my dissolving then is going to be endothermic in place of exothermic. And my delta H is going to be positive, okay? So if that's the case, is it possible for something like that to dissolve? I mean, you know, salt dissolves in water. So if delta H is positive, that doesn't easily contribute to a delta G being negative. So what has to be true? Well, what has to be true then is as long as the entropy, because remember, this is positive. I want this to be negative. This number will end up negative as long as this term is sufficiently large enough to overpower this one. So as long as my entropy is either increasing or staying the same, this term is going to be negative. And so the linchpin, basically, the most important piece is the temperature. If the temperature is high enough, then this term will be big enough to overpower this positive term, and then the delta G will be negative. So if I've got endothermic dissolving, I will have a negative delta G if my temperature is high, but if my temperature is low, I'm going to end up having a positive delta G. Okay, this is actually the situation with most ionic substances, and we tend to dissolve a lot of them in water. So as long as the temperature is high enough, the substance will go ahead and dissolve. Okay. Now, as you're going through this, again, I'm going to caution you, keep in mind, they're not always solid solutes with liquid solvents. Sometimes they're different types of solutes and solvents. So you've got to keep that in mind. Let's look at example 5.3 together. A solute is dissolved in a solvent for which the solute-solvent attraction is small compared to the solute-solute and solvent-solvent attraction. Okay, so let's stop there for a second. What does that mean? Solute-solvent attraction is small. So that means the particles don't really want to interact with each other. They'd rather stay with their own kind. The solute would rather stay by itself. The solvent would rather stay by itself. I got to cram them together in order to make them want to dissolve. And so because that's going to require energy, that's going to make my delta H positive because I've got to put energy into it. It's not going to give any energy off. It's going to require energy. So my delta H is going to be positive. Okay, so I'm going to make that note to myself here that the first sentence of this problem tells me that delta H is going to be positive. Then it says, will this solute tend to dissolve better at high temperatures or at low temperatures? Okay, so as long as delta S is positive, as long as that is true, what we had already determined was as long as this is positive, as long as my temperature is high enough, then delta G will be negative. And so the answer here is that this solute is going to dissolve better at high temperatures than it is going to at low temperatures. Okay, let's look at the second part of the problem. So you flip the page over. In the formation of an ideal solution, is delta S positive or is delta S negative? Okay, so an ideal solution, we said that delta H is equal to 0. Well, if this is equal to 0 and I need this to be negative, so this is basically going to drop out. What's going to have to be true? Is delta S going to have to be positive or delta S going to have to be negative? If I need this to be negative and this isn't here, then delta S is going to have to be positive because the whole term is already negative. Okay, so in that situation, for an ideal solution, delta S is going to have to be positive. Okay, so basically the tips that I can give you here, make sure that you have these pieces memorized. okay? You're going to have to know what's the situation if each one of these terms is positive or negative. The other thing that you need to remember is that depending on what your attractions are, if the solute and solvent attractions are smaller than the particles for each other, that dissolving is endothermic and delta H is positive. If those attractions are greater, then the delta H is going to be negative. And so that's going to have to be something that you stick in your memory as well so that you can analyze these different situations, okay? One other thing that I was going to point out to you, and that is that this is the last video that I am making for this particular chapter, but I'm linking you to lots of other videos for the remainder of the chapter because like you, I do not have access to a laboratory where I can show you a lot of the things I would really like to be able to show you. And so I'm finding some other videos that are going to enable you to see some of the equipment and some of the processes that you need to be able to see to understand some of what is going on. So it doesn't mean I'm abandoning you. It just means that I'm providing a different method for you besides my lectures to really learn and understand some of the other material. So enjoy the rest of the chapter. If you need help, make sure you email me, and then I'll see you again in Module 6.